Last time we talked about equivalent resistance, and here we're going to talk about equivalent sources. So what we have here is a model of a practical voltage source, and it consists of an ideal voltage source with zero internal resistance in series with an resistor R1. Likewise, we have an ideal current source in parallel with a resistance R2. And what we want to do is to convert from one practical source into another practical source, in this case a voltage to a current and a current to a voltage. So we want to take this voltage source in series with R1 and convert it into a current source that's in parallel with R2, or take this current source in parallel with R2 and convert it to a voltage source of Vs in series with R1. And the key concept here to do that is that the voltage and current characteristics across A and B are identical for this circuit as well as for this circuit. And that's what we have here, is an IV characteristics associated with the terminals A and B. So let's analyze the top diagram, which consists of an ideal voltage source in series with R1. Here we're going to use KVL. In KVL here, we'll start at this point, Vs at the negative terminal, and we have a voltage rise of minus Vs and a voltage drop of Vr and a voltage drop of V. So the sum of the voltage rise is Vs, and the sum of the voltage drops is Vr plus V. We can substitute Vr for Ohm's law, and in this case this would be I times R1. Solving for I, we have I is equal to Vs minus V, which is just the voltage across resistor R1, and we just divide that by R1. So let's look at how this, and basically this is an equation of a line with having negative slope, and we want to see where it intercepts. So in this case, when we set I equal to 0, where does it intercept on the V-axis? Well, it intercepts when V is equal to Vs. Okay, now we're going to look when the voltage is 0. When the voltage is 0, the current is just Vs divided by R1. So when the voltage is 0, I is just Vs divided by R1. Now we're going to look at the current source and analyze that, and we're going to use KCL. And we're going to take a look at node A, in which we have the incoming current is Is, which is equal to the outgoing current, which consists of IR plus I. We can replace IR with Ohm's law such that this is equal to V divided by I R2, I'm sorry, R2 plus I. And we can solve for I. I is equal to Is minus V over R2. So this is again a line with a negative slope, and the slope of that line is negative 1 over R2 for this bottom graph, and then the slope for this one is minus 1 over R1 based on this equation. Now we do the same thing when I is equal to 0. When does that occur? Well, that occurs when Is is equal to V divided by R2, or Is times R2. And when does V equal to 0? That means I is just equal to Is when V is equal to 0. So here we have these extreme points for this graph associated with circuit having ideal voltage current source in parallel with R2. Now, in order for these to have identical IV characteristics for both circuits for terminals A and B, we must set these equal. This point here must be equal to this point here. So we set IS equal to VS divided by R1. So now we have that relationship. And now we have IS R2 equal to VS. And if we want the same IV characteristics, resistor R1 and resistor R2 have to be equal. That is, R1 is equal to R2. And that's how we convert from a voltage source in series with R1 with a current source in parallel with R2. And we note that these are equivalent if the resistors are equal, and that we set IS equals to VS divided by R1, and VS is equal to IS over R2, which are just identical relationships since R1 is equal to R2 in order for make these circuits across AB to have identical IV characteristics. So let's do an example of equivalent sources. Here we want to convert the practical voltage source in an equivalent current source. And in this example we have a 50 volt battery in series with a 10 ohm resistor, and we want to convert it into a parallel resistor. With a current source that's also in parallel with it. So here's our parallel resistor, and here's our current source IS. Let me clean this up a little bit. So we have IS, and then we note that this IS is equal to just simply 50 volts divided by 10 ohms, which is equal to 5 amps. And our resistor is just 10 ohms. So that's how you convert very simply a voltage source in series with 10 ohms with a current source in parallel with 10 ohms. Again, we note that the terminals across A and B will be identical to the one here with the current source in parallel with the resistor. So this is terminal A and this is terminal B. It has the same current and voltage characteristics associated with that device. Okay, so the IV characteristics shown here and here is identical to the one with the current source.